Hello, welcome back. This is the ASME Dynamic System Control Division podcast. I'm the host, Hao, Associate Professor at North Carolina State University. In today's episode, we are very honored to have Professor Santosh Devasia from University of Washington as our guest. Welcome, Santosh. Could you please give some introduction about yourself?
Hi, first of all, thank you, Hao-Su, and to your colleagues, for inviting me to the podcast, and for your service to our ASME division. I think this podcast series has been very successful, and a lot of people have been listening to it, and we feel very grateful that you started this, and it's been so active. So thank you.
Thank you.
So I'm Santosh Devasia. I'm a professor of mechanical engineering at the University of Washington in Seattle. I work mostly in the controls area with a variety of applications over the years.
Cool, thank you. Thank you for joining us. Over the last few decades, you have developed a highly regarded research program in the broad area of control, as you mentioned, and your research covers a wide range of applications, I think including nano positioning, manufacturing, networks, robotics, including wearable robots. Can you share with us how you started your journey as a junior faculty and how your research interests evolved over the years?
As a junior faculty, you're always trying out many things, and then trying to see what works. And so it's always hard when you start. But I think I would say in my case, it has always been driven by trying to figure out how to solve a practical problem that I found interesting. That's usually how I still work.
Yeah.
So I think when I started out, my initial research was on nano positioning. And this was because I had a friend when I was a graduate student at UC Santa Barbara. He was doing material science PhD, and he mentioned that he was using an atomic force microscope to look at surface processes. And he told me that the microscope was too slow. By the time he finished measuring, the surface would change. And so at that time, UC Santa Barbara had a robotics center, which was where I was working at that time as a PhD student. And the AFM, the atomic force microscope company called Digital Instruments, was just next door, actually the same, building next door. So I went over, asked them, why is it not working? So interestingly, the company was very open because it was started by a faculty member from the physics department, And so they said basically the speed is limited by loss of precision. So you have residual vibrations when you try to move the piezo around, and that causes vibration, just like a flexible structure that people have been working with. So. My PhD was on vibration control of large flexible structures, and being a controls engineer, I said, I should be able to figure out how to solve a vibration problem.
Yeah.
And so that led to the research question. My first question I was looking at, how can we increase the speed of such nano positioners while maintaining precision? The key is to maintain precision. So then after I got a faculty position, I started working on it. I must say I was very lucky to have some really incredible students. That's very critical, right, for a new PhD, a new faculty member. And so we were, I think, the first group to show that, dynamic issues in like atomic force microscopes and scanning tunneling microscopes, such as hysteresis or creep and vibrations, we were the first to show that they can be systematically modeled and then corrected. And so essentially we used the inversion theory that we were working on, both theoretically and also in experiment to demonstrate that. And then some of these ideas were then further developed by students, now colleagues, of course, such as Cam, Ginger, Garrett, a bunch of others who developed this further. And many of these methods are now adopted in industry, and even a new company that has been started with that. So that was kind of cool. So I think, most of my research works are motivated by problems in practice. And the interesting thing about working and developing theories to address these practical problems is that first, of course, it has good impact. So that's good as a new faculty member to work on something that has impact. Yeah. And then the cool thing is that, once you extract the basic ideas and you and develop theory, then you can apply to other areas. For example, vibrations and hysteresis are problems found in a wide range of systems, starting from this nano positioning systems that I worked on initially. But also in recent soft robotics, that is the problem. Basically, you have elastic dynamics and you're trying to correct for that, and it's very popular. So you can always apply to other things. Yeah. And then finally, I think you get a sense of satisfaction, when you figure out something that is useful. So I think starting from practical issues is always helpful. So to summarize, on how I got started, I think, basically trying to figure out new theories to address a practical problem. And often this leads to new interesting theoretical problems and applications. And then that keeps the research more interesting. And one thing leads to the other, and that's how it goes, right? So
yeah, yeah. I think you have like one paper about this topic, the control in nano positioning, has more than 1,000 citation, right? That's really pioneering work in this topic. Yeah.
Yeah, so that was my, I guess, initial foray into into the faculty position. But started out with a practical problem that I heard from a friend. So.
Yeah. I think this some kind of like a use-inspired basic research, right? It tackles some like a fundamental, like a real-world problem, but also some like a fundamental research question, right? I think that's really kind of like initially maybe challenging to really find how those two domains can meet together, right? It's practical, but also fundamental, right? I think that's really, really amazing. Yeah.
Yeah, something like what you do too, actually,
Yeah, I hope so. Yeah, so to solve the real world problem, I think will be the ultimate goal, right? To do translational medicine, right? Something like that. I think within those research works, can you also give us some examples of significant accomplishments you are most proud of? Yeah.
Okay. I think usually you're most proud of the things you're doing most recently, I think usually, but if I think about, the most impactful work was probably the development of the inverse for non-minimum phase systems, So, as non-minimum phase systems occurs everywhere. Like you were talking about non-collocation. If you have sensing and actuation, which is non-collocated, then that becomes non-minimum phase. So it's there in soft robotics these days, but disk drive systems, nanopositioners, they all have the same issue. If you have thermal systems, where you're heating somewhere and the sensor is somewhere else, right? You're heating at location else, or you're heating, then that becomes non-minimum phase. So in the semiconductor industry, that was very useful because you have these heaters trying to manage temperature control. In my own case, we also applied it to composites welding, where you're heating from outside and you're trying to heat right at the joint of the welding system. In aerospace, like if you have a vertical takeoff and landing aircraft, it's a classical benchmark non-linear non-minimum phase challenge problem, essentially, to try and control that very accurately. Even for conventional aircraft, the pitch control tends to be non-minimum phase. So in all of these systems, it was usually assumed that you couldn't invert a non-minimum phase system to find the precision control problem. And so Eduardo Baio first showed that you can find bounded solutions using Fourier transforms. But the Fourier transforms method cannot be extended to nonlinear systems. That was the catch, because it's only for linear systems. And so I think the major breakthrough from our group was to develop a Picard type iterative method for inverting nonlinear non-minimum phase systems. And to show that you can indeed find bounded inverses to such system and thereby enable high precision control. And so it led to a few other theoretical questions as well. One was, can you get good precision with this inversion-based method if you have plant uncertainty? So for example, in general, if you have inversion-based approaches to precision tracking, it's a model-based approach, right? So the performance depends on the accuracy of the model. If your models are really good, then you can get extremely high precision with this, and the output tracking is very good usually. However, you also know that if your models are bad, then the inverse tends to be having lots of errors, when therefore your tracking is not so good. And so one of the secondary questions we asked is when should you use model-based inversion, right? Especially when you have modeling uncertainties. And that took me a while, and the solution was we could find bounds on the model uncertainties so that the inversion-based method always improves the performance of a feedback controller, irrespective of the feedback. It doesn't matter which feedback you use. We can show that under certain conditions, the inversion always improves the tracking. And essentially, the idea is that the uncertainty should not be bigger than the size of your plant model.
Okay, I see.
It's a pretty nice answer. And that boils down to saying that you need to know the phase of your system. Your phase error should be less than 90. And so that was the basic idea. And then we developed algorithms with this idea for cases where you have modeling uncertainty that varies with frequency. So typically, most models would be probably good at low frequencies, and high frequencies you have modeling uncertainty tends to grow. And so this was helpful for such practical applications where you have uncertainty in some range and not and good models in the other ranges. Overall, I think that the inversion-based approach for non-minimum phase system enable precision control for a wide range of engineering applications. but I suppose the work that I'm most excited about is the most recent one. So I'm working on network systems now. And in network systems, most of the current control theories seek to achieve consensus. Basically, that means that you want the whole network to achieve a common goal, like point in the same direction or pick something up. But current theories don't address that. What current theories basically do is they try to figure out how to get to consensus. That means at the end of the transition, everybody will be pointing the right direction. So the steady state is good, but they don't address the transition problem. So when you're changing from one configuration to the other configuration, you can lose consensus. And this can cause problems. So what happens is, for example, if you're doing vehicles, a bunch of vehicles in a platoon, for example, when you're changing speeds, your spacing gets bad. Same thing when you're braking, suddenly you can get spacing errors, and that can cause accidents. It can be loss of performance. Similar thing happens when you have multiple robots trying to move flexible objects, like a green composite material.
Yeah.
If you don't have consensus during the transition, then you can get excessive forces and damage on the object itself. And so what sparked my interest was, I was hearing about how the natural birds, when they're flocking, I was hearing about that during a conference, and they were talking about how network theories, which obviously the current theories are all an outgrowth of this early flocking models found in nature. They found that the birds, the networks of birds in the natural nature, are much more cohesive than our engineering models predict. And so there's something off in the model itself, that the birds are doing something better somehow.
Yeah.
So that sparked my interest, and I, started asking the question, how much cohesion can you achieve during transition? Is there like a best possible cohesion, and can you achieve that using a decentralized algorithm? So I think my students and I are very excited about this recent work we're working on. We call it delayed self-reinforcement, or DSR approach. And the basic idea was to say, okay, what is the ideal cohesive behavior? The ideal cohesive behavior is when every agent is moving in the same way during the transition as well.
Yeah.
But that would be so this ideal one is actually the centralized system, where if each agent has information about what you're trying to do from the source, then they will all exactly move in the same way. Like it's like having a traffic light, and the light is known to everybody when it turns on.
Yeah.
So then you don't have this delay that happens, right?
Yeah.
And so that would be the ideal centralized system. And so what we did is obviously that's centralized, so the question is, can you make it decentralized? So we have a way of coming up with delayed versions of using past actions, like your past inputs, to reinforce the agent behavior. And that enables you to approximately implement this centralized algorithm in a decentralized manner. And that enables, highly cohesive behavior even during transitions. And so this doesn't require you to change the network structure or slow the system down or requires additional information. And so that has been very exciting, and we are applying that now to a number of manufacturing problems and also autonomous vehicle problems, as well as trying to understand now, we're trying to go back to the nature problem and to say, the reason I got interested was that we found that, people find the natural swarms are more cohesive than current network theories. And so I and my students, we look forward to understanding this puzzle better, maybe in the next few years or so. That's what so.
Yeah. Wow. I think that's a really broad, like a spectrum, right? From inversion system control and to this network system control. Yeah, that's a really different topics. Yeah. And when you mentioned like this, inversion control, like you aim to identify some like a condition to apply this inversion method. Like, do you need some like experiments to quantify if this satisfies the condition to use this method?
Yeah, typically, of course, if you are doing a model-based approach, you might know that your modeling errors have so many parameter, models can be estimated within certain parameters, how much errors you have in each parameter. And from that, you could estimate the uncertainty that you get in your model. So that's one way.
Yeah.
But often it's done experimentally, so modern, like the Gaussian process regression methods, these are just ideal because they also give you uncertainty metrics as well. They can use a database method to come up with the uncertainty that you have in your model.
Yeah.
So then that's the way you use it to then design the inversion methods or the iterative methods to get good tracking. So so the more recent modern database methods are ideal for this because then you have the uncertainty measures with coming from data as well. So
So is this kind of like a data-driven and model-based method for the overall system, maybe?
Yeah, sort of coming together in some sense. Yeah.
Cool. Yeah. For the next works control, it's kind of like a bio-inspired research. And
Yeah.
when you apply your method, how do you evaluate the performance, with your method, without it? Yeah.
Yeah, so the current network theories basically use neighbor-based algorithms. So each agent is looking at the neighbor and doing some sort of averaging methods. And so when you do something like that, people know that this tends to have diffusive behavior. It's actually models diffusion in thermodynamics, for example. So information tends to decay as you propagate, and you can see that, and that's why the transient performance is not very good. Whereas what we are seeing with our methods now is that we can approximate the wave-like behavior seen in nature. So the information propagates as a wave. And that's why it's so exciting, and so we are trying to, of course, in implementation, you can physically see the difference in the deformation that you see in the structure as you're moving around.
Yeah.
But also we're trying to get a better theoretical understanding to see how does it link back to the diffusion, wave-like behavior in nature, so that's where we are now. So
yeah, wow, that's like a very inspired, but also go back to see its overall performance. Yeah, that's very cool work. Yeah. Also fun, of course. Yeah. And I think in addition to the research work, you are also the director of Boeing Advanced Research Center. I think it's called a BARC Center. Could you share with us about the research and activities in your center?
Sure. The BARC Advanced Research Center, or BARC as we call it, because we have our University of Washington mascot is a dog. It's a
Okay.
So BARC for that.
Makes sense now.
So, yeah, it took a long time to figure out that actually works. So we work mostly on manufacturing problems,
Yeah.
And there are like four main topics. One is automation and semi-automation. So a lot of, interestingly, this high-end aircraft is still, a lot of things are done using manual processes, such as inspection inside an aircraft wing is extremely difficult to do. Yeah. And we're trying to make it semi-autonomous. So that's one of the major works. And then we also do problems in safety and ergonomics. That's the second aspect. This involves, trying to address injuries to hand due to, let's say, manual sanding or composites layup using manual methods. The third topic is obviously composites. Pretty much all the efforts are focused on trying to increase the rate of production while maintaining quality. That's a key challenge for aircraft manufacturing. And then especially since there's a lot of demand for new air travel, and the fleet is also already aging, right? So there's a lot of demand, and so trying to increase the production rate. The last topic we have is data science. And data science, as you know, in almost everything is omnipresent, and it's so also in manufacturing. And we also have a new NSF-funded data center led by Steve Brunton. And so we are trying to collaborate, BARC and that center is collaborating in manufacturing problems. Typically, we have about 10 projects every year. And what's special about that is in each project, we have a couple of faculty often from multiple departments. We have bachelor's, master's, and PhD students. And more importantly, we have Boeing engineers who come every week. Wow. And advise the students on these projects, right, to address as real world problems. So what I find is that the students are really motivated to work on these practical problems, right? Yeah. Because they find the Boeing engineers are coming and they feel it's like a real world problem. So and they feel they can make an impact. So I think they work incredibly hard on these problems, which is kind of cool. Yeah. And so in addition to solving problems, which are what they call as high TRL or high technology readiness levels, and many of our solutions here in the BARC lab has made it into the factory floor. But I also find that these practical problems are very rich and really interesting and challenging theoretical problems. So often, even though the project gets over in a year or so, we have a follow-up project, follow-up research project that we do with PhD students that's led to PhD dissertations. So it's a nice loop between practice and theory, that happens. So I think that's very exciting. Yeah.
Yeah, I think in particular for students, they can really work with engineers, right? And it's not a claim and the real world problem. It's actually a real world problem.
A real world problem.
Yeah. And you mentioned like 10 projects. That's every year you have like maybe different 10 projects. It's kind of different every year. It's kind of way, yeah.
Yeah, some projects tend to be a little bit longer. They go up to 3 years sometimes. Because some of the projects are a little bit longer. Yeah. Or they get, they do one part and then they feel they need to adapt to something else, so that might extend. Yeah. But these are projects where the Boeing engineers feel that this is useful for them and they want to implement it in the next few years. So very highly industrially relevant problems that they want to implement it. So those are a little bit different. That's why the TRL levels are a little bit higher. But the questions that you come from that is really interesting. It's really PhD level research that takes a lot longer, but so we have to find a blending of the funding streams to fund the PhD students. But it tends to really exciting problems, I think.
Yeah. Wow, that's really lucky for the student to do this kind of work with this industry collaboration. Yeah.
I agree. I'm grateful too.
And I also know that you are the ASME Dynamic Systems and Control Division Executive Committee. Could you please share with us your role and activities for our division?
Sure. I just finished my term. It's usually a 5-year term on the executive committee, so I'm just done with it this ACC.
Yeah.
So I feel very grateful to have this opportunity to serve on the executive committee. Our division overall is doing very well, I would say. And that's mainly because we have such an active and engaged membership like yourself, who volunteer for the podcast and make our community stronger. So in the past few years that I've been on the committee, I noticed that our division members have launched 2 new journals. One is the Autonomous Vehicles and Systems Journal, and the other is the division's letters in Dynamic Systems and Control, which I think is spectacular, considering we only had like 1 journal before, right? So, and then the Mechatronics Journal as well. And then the members, worked with the American Automatic Control Council to launch a new MEC, which is the Modeling, Estimation, and Control Conference. So that's also coming from our division. We have a great newsletter, I think. Our website is looking very good, much better than before. It has improved substantially with the effort from our members. And the podcast that your group has been running has been awesome, I think. So, I think I'm grateful. I know to have the opportunity to work with all of you and make our division a better place for all of us, right? And the division, I think, is always looking for new ideas. The division has money, by the way, to help support initiatives. So if you have some idea, to improve, especially if it's like, trying to increase the impact on students or outreach activities, the division will provide funding for those kind of activities at the conferences or otherwise. So if you have ideas, please don't hesitate to reach out to the division leadership and and try to help the division. So I think I'm not sure I did anything special. It's just that I tried to make sure that I can help facilitate these processes. But I think overall it's our membership that does most of the work, and I think we have a wonderful membership. I think that makes our division so good.
Yeah. I think it's really great to see the field is growing and also the division is growing. And I think, as you mentioned, the several initiatives from our division, I think in particular the journal papers, I think we really have like a long-term impact, really promote the research education, right, for our field. That's really, really helpful to further grow this community. Yeah.
I agree. And thank you for you as well, for helping out on that. So.
Sure. Yeah, I think maybe I have one last question I want to ask you. Like you have, I know you mentored many students, and quite some of them are already professors in many universities. Do you have something maybe secret to share? How do you mentor students? Why you have many students who are professors right now? Yeah.
I think I have maybe half the students I've advised joined academia, and the other half is the industry.
Yeah.
I'm not sure I mentor either group any differently because those in industry are also doing research type activities, right? So I think perhaps the difference I find is that, on students joining industry versus academia seems to be that, some of them enjoy teaching, so they figured this out when they're a TA most probably. And some of them enjoy the freedom that comes with the job. So, I personally enjoy both teaching and the academic freedom that we get, right? So with the job. Yeah. And so I think this is the advantage of being a faculty member with tenure. Maybe this happiness of being a professor, I am very happy to be a professor. That's on some of those students, right? And so when the student decides to apply for academic position, I usually do that when I meet with them every year. I meet with my students for discussing professional development approaches. So this is just for their professional development. So I have a lunch with them in the summertime, and I spend time talking to them about their future plans. And if they tell me that they're interested in being a faculty member, then I do spend some time after that talking about what it takes to be succeeding in academia. Right. I start very early on their future research plans, to saying how they can link what they're doing to potential new directions. Yeah. And most importantly, I think as a faculty member is reviewing their presentation for job interviews and working on that. I'm sure my advisor helped me out on that, and that was useful, right?
Yeah.
So, but I think most students I've had were self-starters, I suppose my key is to try and advise them rather than lead them, So I think maybe in the very beginning you're leading them a little bit, but hopefully towards the end you're just discussing like colleagues. At that point, they'll be successful.
Yeah.
But I think it's mostly the students helping me out rather than me helping them out. I think. So that's really the key, I suppose. And eventually, if they're self-starters, they become successful by themselves. So
Yeah. It's a kind of like an organic growth cycle, like both for the weather and also students that can learn from each other. Yeah.
Exactly. And it's fun to be a professor, I think. So
yeah. I think that's a major privilege, right? Being a faculty member.
It's a pleasure to see them, always. So.
Yeah. Cool.
Fine.
Yeah, thank you for sharing your experience and the perspective. Really appreciate your time. Hopefully, we'll see you in person soon. Yeah.
Thank you, Hosu.
Cool. Yeah, thank you.